So how do we find the eigenspaces and eigenvalues for a linear transformation? Well, we need to make this into somehow a question about solving a linear system of equations. But the big shift that we usually make at this point in linear algebra is that whereas up until now we've been mainly concerned with solving systems of equations ax equals b, where the right-hand side is a known vector and my unknowns are an unknown vector and my matrix appears in only one place. What we want to do now instead is ask a question, well, if I, for some reason, believe that my linear transformation has an eigenvalue of 2, if I know that it's doubling the lengths of some vectors without changing their direction, I can then ask the question, which vectors are being doubled by this linear transformation? For which vectors v is it true that a times v is just equal to 2 times v? Right? On which vectors does my matrix, which is a complicated object, actually behave just like a single scalar, which when I multiply it by a vector does nothing but change the length of the vector without changing its direction? So the new types of equations we're going to be more interested in solving look more like a times v equals a constant times v. This is going to be our new area of focus with the algebra. This is called the Eigenvalue-Eigenvector Equation. Eigenvalue-Eigenvector Equation, where this number, this scalar lambda, is called the eigenvalue in this equation. That's the stretch factor. It's how much my linear transformation is multiplying the length of a vector by. And then any v that satisfies this equation is going to be called an eigenvector. And as we were talking about a moment ago, eigenvectors don't just come in isolation. They live in entire eigenspaces. Right? These systems of equations don't just have one solution. We want them to have infinitely many solutions. And that actually is the key to figuring out how to solve the eigenvalue-eigenvector equation. We need there to be infinitely many solutions. And the reason that we need infinitely many solutions is that we don't want there to just be one vector that satisfies AV equals lambda v, because there is always one vector that satisfies AV equals lambda v, namely if v is the zero vector. Because if v is the zero vector, then the left-hand side of this equation is going to be the zero vector, and the right-hand side is going to be lambda times the zero vector, which is the zero vector. So of course the zero vector always solves the eigenvector-eigenvalue equation. And so the key is we need there to be infinitely many solutions so that 0 is not the only solution. So we're never going to let 0 be an eigenvector. 0 is going to belong to every eigenspace, but we're never going to let it be an eigenvector. It's always the bridesmaid and never the bride here. So if we want this equation to have infinitely many solutions, let's see if we can figure out how to make that happen. Well, first we need to turn this equation into something that looks more like one of these, right? Because we only really know how to solve these kinds of linear systems of equations. So we need to turn the former into the latter somehow. And to make that happen, what we're going to do is just subtract the lambda v from both sides. So if I subtract lambda v from both sides, AV minus lambda v is going to equal the zero vector. So now the right-hand side of my equation is just a vector. Left-hand side, well, now left-hand side has a couple different terms in it, but both of these terms have the vector v in them. So let me factor that v out. If I factor the v out, then the matrix, which is here in the cofactor, is going to be A from my first term minus lambda, which is my unknown eigenvalue, right? If I don't know in the beginning what that is. But then I need a matrix here because I can't subtract a number from a matrix. And so I just need a matrix for which it is true that that matrix times lambda times v is the same as lambda times v. Well, the only matrix which I know which does that is the identity matrix. So now we've put this into a form that looks like one of the kinds of linear systems that we know how to solve, right? Our right-hand side is the zero vector. My left-hand side is a matrix, some matrix times some unknown vector. Right? And so I know now that I can solve this system using the tools of, let's say, an augmented matrix. Right? With a zero vector on the right-hand side and A minus lambda times the identity on the left-hand side. So if I can find the reduced row echelon form of this, then I'll be able to find the solution set of this, which is the same as the solution set of that, which is the same as a description of all of the eigenvectors of this matrix. But I need this to have infinitely many solutions. And if I need this to have infinitely many solutions, here's the kicker. If I need this to have infinitely many solutions, that means that I need for A minus lambda times the identity not to be an injective linear transformation. In other words, I need there to be at least one column of the reduced row echelon form which does not have a pivot. I need a non-pivot column. That's the only way I'm going to have infinitely many solutions for this system. Well, how do I get a non-pivot column? I'm only going to get a non-pivot column if I also get a non-pivot row. Because after all, my matrix A here is a square matrix. We're always starting with a square matrix when we're asking eigenvalue-eigenvector questions because we want the domain and the codomain to be the same vector space. So A is always going to be a square matrix. So if I need a non-pivot column, I can get a non-pivot column by having a non-pivot row. There's no way to have one without the other if my matrix is square. But if I have a non-pivot row in a matrix is just a row in the reduced row echelon form which is all zeros. So another way to see what this means is we need, for the reduced row echelon form of A, to have a row of all zeros. REF of A has a row which is all zeros. Maybe it's the last row, who knows? Oh, sorry, not reduced row echelon form of A. I want the reduced row echelon form of A minus lambda times the identity. I don't want to get those two confused. So it needs to have a row of all zeros. But now here's my question. What is true about the determinant of a matrix which has a row of all zeros? One way to think about the determinant of a matrix, one of whose rows is all zero, is let's say I took this row of all zeros and I multiplied it by 17. That would not change the entries on the row at all, right? Because 17 times 0 is just 0. But that operation has to change the determinant of my matrix by a factor of 17. So if multiplying by 17 changes the determinant by a factor of 17, but it doesn't change the entries on my matrix at all, that must mean that whatever the determinant of this matrix is must be equal to 17 times its own determinant. So the determinant is something which doesn't notice when I multiply it by 17. D times 17 is equal to D. Well, there's only one real number in the universe which doesn't notice when we multiply it by 17. That number is 0. So if we need the reduced row echelon form of this matrix to have a row of all zeros, this must mean that the determinant of my matrix is 0. And this is the magic. I'm going to put a box around this, and then we'll talk about what the practical import of this is. And that's where we're going to wrap this up today. So this thing in a box here, the determinant of A minus lambda I equals 0, is what ensures a non-pivot row in this, which ensures infinitely many solutions to this equation, which ensures a non-zero solution to this equation, which is what we want. So the first thing we observe is that we're going to be able to find eigenvalues and eigenvectors by finding non-zero vectors v, which solve the eigenvector-eigenvalue equation. And the way we get that is by writing down this equation. Determinant of A minus lambda times the identity is equal to 0. That's called the characteristic equation for the matrix A. Determinant of A minus lambda times the identity is equal to 0. And so how we use this is that we're trying to solve the eigenvector-eigenvalue equation. AV equals lambda v. The numbers, lambda, are going to be my eigenvalues. And so we can use this characteristic equation to find the values of lambda. And then once I know what the values of lambda are, I can use this row reduction to find the solution set of this equation. So there's the recipe for what we're going to do. First, solve the characteristic equation, determinant of A minus lambda I equals 0, to find the eigenvalues. the lambdas, the stretch factors that make this work. And the second thing we'll do is then use reduced row echelon form of this to find the solution set, which is the eigenspaces. So let's step through an example of doing each one of those things, and then I'll give you one to work on with your group, and it'll be a good place for us to wrap up. So suppose that I have this 3 by 3 matrix, 3, negative 3, 1, 0, negative 4, 2, 0, 0, 7. If I want to know what the eigenvalues of this linear transformation with this standard matrix are, then I want to solve the characteristic equation. Determinant of A minus lambda times the identity is equal to 0. So what that tells me to do is first figure out what is the matrix A minus lambda times the identity. Remembering that the identity matrix just has 1s on the diagonal and 0s everywhere else, what this is really asking me to do is just subtract this unknown lambda from each of the diagonal entries of my matrix. So instead of 3 on the diagonal here, I'll have 3 minus lambda. Instead of negative 4, it's negative 4 minus lambda. Instead of 7, it's 7 minus lambda. All the other entries in this matrix remain the same because all the other entries in the identity matrix were 0. So subtracting 0 is invisible. So I start by subtracting lambda from every diagonal entry of my matrix. Then I need to take the determinant of this 3 by 3 matrix, which now has unknowns in it. So this step is sometimes scary, right? But we have the shrink ray at our disposal. If I factor out a 3 minus lambda, I can use the shrink ray to nuke the first row and first column of this at the expense of having a factor of 3 minus lambda in my determinant. Then I'll have a negative 4 minus lambda. I'll have a 2 by 2 determinant to do from over here, from which I'll factor out a negative 4 minus lambda, nuke the first row and the first column of that 2 by 2, and give me a 1 by 1 with only 7 minus lambda as the entry. So this is the thing, the shortcut that Debano was mentioning a few minutes ago. This is an example of a matrix which is upper triangular. All of the numbers below the diagonal entries are all 0s. And so it turns out that the determinant of this matrix is nothing more than the product of the entries that are on the diagonal. So that's a little shortcut for this, but again, I favor the shrink ray as a way to do it in general. But anyway, we take the determinant of this matrix and we get the polynomial 3 minus lambda times negative 4 minus lambda times 7 minus lambda. And the characteristic equation says set that equal to 0 and solve it for lambda. And if you're going to do that, I would recommend not multiplying it all out. I would leave it in its factored form. Because when it's in its factored form, because the right-hand side, the other side of the equation is 0, we can tell that this must mean that 3 minus lambda is equal to 0, so lambda could be equal to 3. Negative 4 minus lambda is equal to 0, so lambda could be negative 4. Or 7 minus lambda is 0, so lambda could be equal to 7. Right? So this polynomial equation has 3 solutions, negative 4, 3, and 7. Those solutions are the eigenvalues of this matrix because they make the characteristic polynomial, determinant of A minus lambda I, equal to 0. That's the case because if I subtract any one of these entries from all the diagonals of my matrix, the result is going to be a matrix which is not an injective linear transformation, and so its homogeneous equation will have infinitely many solutions, and that infinitely many solutions in my solution space is going to be the eigenspace associated with that eigenvector. So the step 1 is to find the eigenvalues the way that we did in this example. Step 2 is to find the eigenspaces. We can do that by finding solution sets for the associated homogeneous equation. Let's walk through an example of that from the last section of this chapter. Suppose that you hand me a 4 by 4 matrix, and we do the whole process of figuring out what the eigenvalues are by solving the characteristic equation, and we find out that one of the eigenvalues is 2. So that's where we're kind of starting this problem. If we start out by knowing one of the eigenvalues is 2, how do I find a basis for the eigenspace? Like, what are the vectors that this 4 by 4 matrix is merely stretching by a factor of 2 without changing their direction? Those are going to be the solutions to the equation AV equals 2V. Or a better way to say that is it's the solutions to the vector equation A minus 2I times V is equal to 0. In other words, this is the kernel of the linear transformation whose standard matrix is A minus twice the identity. And we know how to find kernels. This was a topic from chapter 4, right? So to find the kernel of this linear transformation, I'll just subtract 2 from all the diagonal entries. So take 2 away from 4, 3, 2, and 2. I'm going to get this 4 by 4 matrix over here. And to find a basis for its kernel, we'll just augment it with a 0 vector and find the reduced row echelon form. And in my reduced row echelon form, remember, I'm expecting to see at least one column which does not have a pivot. And sure enough, in my example here, column number 3 does not have a pivot. Therefore, this third column corresponds to the z variable, right, is going to be my free variable, and all the other variables are going to be bound. So in equations form, this reduced row echelon form would be x, y, and w all equal to 0, but z is free. Z can be any real number a. And so the solution set is the set of all vectors having the form 0, 0, a, 0 for any real number a. And so a basis for that solution space, which is the eigenspace associated with the eigenvalue of 2, that basis can be 0, 0, 1, 0. So that's kind of the overall shape of how to find the eigenvalues and the eigenspaces for a square linear transformation. To find the eigenvalues, set up the characteristic equation by subtracting lambda, an unknown lambda. You can think of it like an x, right? I don't know why historically we use a Greek letter for this. We're subtracting some unknown lambda from each of the diagonal entries. Then take the determinant of that matrix that results. That determinant is going to have a bunch of lambdas in it. It's going to give you a polynomial expression. This polynomial expression is going to have a degree equal to the number of rows in my matrix. So because we had a 3 by 3 matrix, we end up with a cubic polynomial for the characteristic polynomial, which is usually bad news because we usually don't know how to solve cubic polynomial, quartic polynomial, nth order polynomial equations. We're much better with quadratics. So the 2 by 2 cases are the nicest ones. But we just happen to get lucky here, right? Because my determinant was already factored by the time I computed it. And so to find what values make that determinant equal to 0, we can just use the 3 factors and figure out what lambdas make each of those factors 0. And so we end that process with a list of the eigenvalues of our matrix. Then we would take each one of those eigenvalues and do this process, where we find a basis for the solution set of the homogeneous equation associated with a minus that number times the identity. So we do that by subtracting that number from each of the diagonal entries, and then using our kernel finding process, solve the homogeneous equation, and we expect there to always be a non-pivot column. We need at least one free variable. Otherwise, we haven't gotten infinitely many solutions, which would mean that the only solution to our eigenvector-eigenvalue equation would have been the 0 vector, and we never want the 0 vector to be an eigenvector. So we want there to be at least one free variable in this process. In this example, it was z. And then by using our usual process of finding the basis for the solution space, we find a basis for the eigenspace associated with each of these eigenvalues.